Okay, so this video is about buffers. A buffer is a solution that can resist changes in pH with small additions of acid or base. So I'll write that and try to say it again at the same time. A buffer is a solution that can resist changes in pH with small additions of acid or base. So if you were just to take distilled water and add acid or base to it, pH changes very rapidly. We know that pH changes in a logarithmic way. So obviously it depends what concentration acid or base you add to it, but the pH of that distilled water would change quite quickly. However, if you have something that we refer to as a buffer and you add acid or base to it, the pH actually stays largely the same for a given amount of solution that you add, and then eventually the pH will change, which is why the inclusion of this word small is very important for your IB definitions. It's usually underlined. The buffers are super important all over the place, bodies of water, inside of you, inside of other living things, because there are many, many processes and especially many enzymes, which is for the living things part, that are highly pH dependent. And if you are in too acidic environment, the H plus ions will bond with the enzyme and change its shape, or the OH minus ions in a basic environment will pull H's off of the enzyme and change its shape in a different way. So being in the wrong pH environment can be very harmful to enzymes. It can denature them and make them ineffective at doing their jobs. So here's our definition once again. A buffer works by being able to neutralize small additions of either acid or base. And if you're going to neutralize an acid, you need to contain base. And if you're going to neutralize base, you need to contain acid. So the way that a buffer works is it contains both a weak acid. It contains both a weak acid and its conjugate base, or it contains a weak base and its conjugate acid. Okay, so it's going to have to contain both of those things in relatively high amounts. You can make acidic buffers that maintain pH somewhere below 7, and you can create basic buffers which hold the pH somewhere above 7. The acidic ones are created by weak acids and their conjugate bases, whereas basic ones are produced by weak bases and their conjugate acids. And there's going to be two different methods for making a buffer. The simplest would be to use whichever weak species you're beginning with, and then add salt of its conjugate. The other way is to start with a weak species and add a strong version of the opposite species. So like if you start with a weak acid, add strong base to it, but only add half the moles of strong base, and that will end up giving you both conjugate, the weak acid and the conjugate base in relatively equal amounts. And I'll walk through each of these methods a little bit more closely now. So if you have a weak acid, we know that it only partially dissociates, and therefore mostly in a bottle containing a weak acid solution, most of it is in this molecule form, in this undissociated weak acid form. On the other hand, if you take a salt of the conjugate base of this weak acid, so here's the conjugate base, ethanoate. If we take a salt that contains that conjugate base, we should know by now that that should have a little bit of a basic character to it. And this salt is highly soluble, which means that if you put it into water, it's going to completely dissolve and give you a lot of CH3COO minus ions. So if you take those two solutions and you mix them together, if you take the weak acid solution and this salt solution and you put them in the same flask, now you're going to have a solution that has a lot of this weak acid molecule, but it also has a lot of this weak base molecule. So it's going to have a lot of both. And ideally, it's going to have equal amounts of both. Because what's going to happen if we add H+, if you look at this equilibrium, you should see H+ is here. It's on the right-hand side. So if you add H+, the H+ is going to react with the ethanoate, the conjugate base ions, and it's going to shift left, and it's going to produce weak acid molecules. So we're going to react with the conjugate base ions. That's going to cause a shift left, which will produce more weak acid molecules. But remember, pH doesn't depend on how many weak acid molecules there are. It depends on how many dissociated ones there are. how many H plus ions there are. So when you add a new H plus ion, it pretty much gets grabbed up by the conjugate base immediately and turns into the weak acid molecule, and therefore there is no significant change in H plus, and therefore no significant change in the pH. So if you add acid to this, it will continue to get neutralized by the conjugate base until you run out of conjugate base. So you couldn't do this indefinitely, but you could do it for a small amount of acid. Same idea if you add base to this solution. So if you think about adding OH minus, you can think about it in a couple different ways, but I'd probably think of it as OH minus will react with H plus to produce water. This removes H plus from the system, and this will cause a shift right to replace it based on the equilibrium. So for each H plus that gets neutralized, another is dissociated, and therefore you're going to have no real change in pH. For every OH that gets added, an H plus will get used up, but you have weak acid molecules here that can resupply more H plus. So again, for a small amount of OH minus that you're adding, you're not really going to change the pH of the solution because the H plus amounts are staying the same. So that's how a buffer works. If it can have both an acid and a base in the solution in equal amounts, then it can neutralize equal amounts of acid and base. A basic buffer would work the same way, except you begin with a weak base and then its salt of its conjugate acid and get a solution that contains both, and therefore we could do the same thing. If we added H plus will react with the OH minus to produce water, and then more of the NH3 will react and form more OH minus on this side, keeping the amount the same. If you add more OH minus, it will react with the NH4 plus and shift left, keeping the OH minus amount pretty much the same. So the other way to make the weak acid or base is to start with just the weak species and then add some strong stuff to it. In the end, you're really going to end up with the same idea as before. You're going to end up with a weak species and its conjugate salt. You're just getting there a different way. So if you start off with 1 and you start off and you add half as much of this, then the change is that this one's going to lose half a mole, and this one's going to lose half a mole as they react because they'll react completely. And when you're done, you'll be left with 0.5 of the weak acid still remaining. You'll have 0 of the base left over, but you'll have also made 0.5 moles of the conjugate on the other side. So the conjugate would be this thing. So this is the salt that's produced by this reaction, and you start off with 0 of it. As these get used up, the strong base will be entirely used up. You'll still have half a mole of weak acid. You'll have made a half a mole of its conjugate base, and therefore you've made a buffer. You've made something that has equal moles of weak acid and its conjugate in the same solution. You could do the same thing here with a weak base. If you add half the moles of HCl, you'll be left with half the moles of NH3 and an equal number of moles of NH4 plus on the other side. So it's just an alternative way to make that same combination of a weak something with its conjugate in solution. Things can affect buffers. If you dilute a buffer, it will actually still maintain pH around the same pH. It won't affect the pH because you're going to dilute both the weak species and the conjugate species by the same factor. But it will affect the buffering capacity, which is the amount of acid or base that the buffer can neutralize, because you've lowered the concentrations. So when you add acid or base to it, it can't as effectively neutralize it anymore. Temperature has the potential to affect a buffer's pH because it can cause equilibrium shifts, and pressure can possibly affect a buffer's pH as well if it involves gases. But these are not really factors that they're probably going to get into so much. Just to know that they can affect the pH is probably more than enough. But dilution, pH that it maintains is the same, but its buffering capacity goes down.